Today, we embark on an extraordinary journey to unravel one of the most profound mysteries that has fascinated humanity across millennia: time itself. What is time? How do we experience it, measure it, and understand its elusive flow? In this video, we will explore the science behind time, peeling back layers of physics, philosophy, and human perception to reveal the hidden truths about this intangible dimension that governs our lives. If you find this journey as captivating as I do, please like and share this video to invite others to explore the mystery with us. Time is a concept so fundamental that it often slips past unnoticed in daily life, yet it shapes everything: our memories, our plans, the rhythms of nature, and even the laws of the universe. We experience time as a continuous flow, moments unfolding into one another, past leading to present, present marching into future. Yet, when we try to pin down what time really is, clarity escapes us. Is time an absolute entity that flows independently? Or is it something woven into the fabric of space and matter? Our first step is to understand time as a measurable quantity. Ancient civilizations observed the regular patterns of the sun, moon, and stars to mark the passage of days, months, and seasons. The earliest calendars and sundials emerged from the human need to predict cycles, planting seasons, tides, and celestial events. These tools allowed societies to organize life around time's steady pulse. Yet, time is more than a practical tool. It is deeply embedded in the laws that govern the cosmos. Isaac Newton envisioned time as absolute and universal, flowing at a constant rate regardless of observers. In his view, time marched onward like a relentless river, unaffected by the events within it. For centuries, this Newtonian notion prevailed, guiding scientific thought and everyday understanding. But the dawn of the 20th century brought revolutionary insights that would forever alter our grasp of time. Enter Albert Einstein, whose theories of relativity challenged the idea of absolute time. According to Einstein, time is relative, intertwined with space itself, in a four-dimensional fabric called space-time. The passage of time depends on the observer's motion and gravitational field, bending and warping with velocity and mass. This revelation was stunning. Time was no longer an independent backdrop, but a dynamic player shaped by the universe's geometry. Clocks moving at different speeds tick differently. Gravity, which bends light and curves space, also slows time itself. This phenomenon, known as time dilation, has been experimentally confirmed countless times, from precision atomic clocks on airplanes to satellites orbiting Earth. Thus, time became an elastic dimension, stretching and compressing with the cosmos. This understanding opened new vistas in physics, linking time to the fundamental nature of reality. Beyond physics, time profoundly influences how we experience life. Our perception of time's flow is deeply subjective. Moments of fear or joy can make seconds feel like minutes or hours pass unnoticed. The brain constructs time through a complex interplay of memory, attention, and sensory input, creating the narrative that binds our past, present, and future. Philosophers and scientists alike ponder whether time is real or merely a mental construct. Some argue that time exists only as a sequence of events experienced by conscious beings. Others maintain that time is a fundamental aspect of the universe, existing independently of observation. As we journey deeper, we will explore how quantum mechanics, the strange realm of the very small, reshapes our understanding of time. Quantum theory suggests that at the most fundamental level, time may be discrete, made up of tiny indivisible units, challenging our classical continuum. We will also look at how time shapes life on Earth, regulating biological rhythms from the beating of our hearts to the cycles of sleep and wakefulness, and how disruptions to these rhythms impact health. Moreover, time's arrow, the directionality from past to future, raises profound questions. Why does time flow in one direction? How does entropy, the measure of disorder, connect to this flow? These mysteries lie at the heart of thermodynamics and cosmology. In the coming parts, we will weave these threads together, blending physics, biology, psychology, and philosophy into a rich tapestry that reveals the multifaceted nature of time. So join me as we step into the river of time to discover its currents, its depths, and its infinite horizons. Building upon our initial exploration, we delve further into the measurable and physical nature of time, beginning with the fundamental tools humans have devised to track its passage. The earliest timekeeping devices, such as sundials and water, clocks, reflect our innate desire to grasp the rhythm of the world. These primitive instruments transformed time from a flowing, intangible experience into something concrete, a sequence we could count and measure. As civilizations advanced, the need for ever more precise timekeeping grew. Mechanical clocks emerged in medieval Europe, their intricate gears and escapements marking the relentless march of seconds and minutes. The invention of the pendulum, clock in the 17th century by Christian Huygens, dramatically improved accuracy, allowing scientists and navigators to coordinate events with unprecedented precision. Precise measurement of time became essential, not only for daily life, but also for science and exploration. Navigators relied on accurate clocks to determine longitude at sea, revolutionizing travel and commerce. Astronomers timed celestial events with increasing exactitude, unlocking the secrets of the heavens. The quest for perfect timekeeping culminated in the development of atomic clocks in the mid-20th century. Unlike mechanical clocks, atomic clocks use the natural vibrations of atoms as their ticking mechanism. Cesium atoms, for example, oscillate at an incredibly stable frequency, allowing these clocks to keep time with astonishing precision, so precise that they lose only about 1 second every millions of years. This leap in accuracy underpins much of modern technology. The Global Positioning System, GPS, relies on atomic clocks aboard satellites to triangulate positions on Earth with incredible accuracy. Telecommunications networks synchronize data transfer using precise timing protocols derived from atomic standards. Even financial markets depend on exact timestamps to regulate trades. But beyond practical applications, atomic clocks reveal deeper truths about time itself. Experiments placing atomic clocks on airplanes have demonstrated that moving clocks tick slower compared to stationary ones, confirming Einstein's theory of relativity in a tangible, measurable way. This intersection of theory and experiment marks a profound transformation. Time is no longer an absolute, universal constant, but a dynamic quantity affected by speed and gravity. The implications reach far beyond clocks. They reshape our understanding of reality, space, and causality. This realization leads us to the four-dimensional continuum of space-time. In this framework, space and time are inseparably linked, forming a fabric that can bend, stretch, and warp. Massive bodies like stars and planets curve space-time around them, influencing how time flows. The closer you are to a massive object, the slower time passes relative to a distant observer. Consider a clock on the surface of the Earth versus one on a satellite in orbit. Due to Earth's gravity, the clock on the surface ticks slightly slower, a difference that must be accounted for to ensure GPS accuracy. These effects, though imperceptible in everyday life, accumulate to significant discrepancies in high-precision technologies. Time's relative nature challenges our intuition. We often think of seconds, minutes, and hours as universal units, the same everywhere and always. But in truth, time is elastic, a shape-shifting dimension influenced by motion and gravity. This leads to the mind-bending consequences of Einstein's special relativity. When objects approach the speed of light, time slows dramatically for them relative to stationary observers. This time dilation means that astronauts traveling near light speed would age more slowly compared to people on Earth. The implications are profound. They suggest that past, present, and future are not fixed, absolute realities, but depend on the observer's state of motion. The universe becomes a tapestry where time is woven differently, depending on perspective. Such ideas provoke deep philosophical questions about the nature of reality and causality. If time can stretch and contract, what does that mean for our experience of free will, memory, and destiny? Furthermore, these insights open pathways to understand exotic cosmic phenomena like black holes. Within a black hole's intense gravitational field, time slows to an extreme. To an outside observer, anything falling in appears frozen in time, while inside, time may behave in unimaginable ways. The fusion of time and space into space-time invites us to reconsider the nature of the universe itself. Is the flow of time fundamental, or does it emerge from deeper, timeless laws? As we continue, we will journey into the quantum realm, where particles behave unpredictably and the classical picture of time is further challenged. Quantum mechanics introduces concepts of superposition and entanglement that strain our classical understanding of cause and effect, and time. Our understanding of time remains incomplete, but each discovery illuminates a new facet of this eternal mystery. As we venture into the quantum realm, time reveals yet more of its enigmatic nature. Classical physics, including Einstein's relativity, provides a coherent picture of time on large scales, from planetary orbits to the fabric of space-time. However, when we probe the subatomic world, the very building blocks of matter and energy, our understanding of time becomes less certain, more mysterious. Quantum mechanics governs the behavior of particles at scales unimaginably small, electrons, photons, quarks, and introduces a universe fundamentally different from everyday experience. Here, particles exist not as discrete points with defined positions and velocities, but as probability waves, described by a mathematical entity called the wave function. These waves evolve over time according to the Schrödinger equation. Yet, this evolution presents puzzles when viewed through the lens of time's arrow. At the heart of quantum theory lies an apparent paradox. The equations governing wave function evolution are time-symmetric. They work the same forward or backward in time. Yet measurements collapse these wave functions into definite outcomes, a process that appears irreversible and introduces a directionality to time, much like the arrow we observe in classical thermodynamics. This measurement problem highlights an unresolved question. Why does time seem to flow in one direction, from past to future? What gives rise to this asymmetry when fundamental laws do not mandate it? Some physicists propose that the act of observation, or decoherence with the environment, breaks the symmetry, making the future distinct from the past. Furthermore, the quantum world suggests time may be quantized, composed of discrete, indivisible ticks, rather than flowing smoothly like a continuous river. This idea remains speculative, but theories of quantum gravity seek to unify quantum mechanics with general relativity, potentially revealing a granular structure of spacetime at the Planck scale, an unimaginably tiny length scale where classical concepts fail. Attempts to reconcile these realms lead us to concepts like loop quantum gravity and string theory, both striving to describe the fabric of the universe where time and space emerge from more fundamental elements. In these theories, time might not be fundamental at all, but an emergent property arising from deeper, timeless laws. Moreover, the concept of entanglement in quantum mechanics defies classical notions of locality and temporal order. Entangled particles influence each other instantaneously over vast distances, seemingly outside of space and time constraints. This phenomenon challenges our understanding of cause and effect and hints at a deeper interconnectedness within the universe. Philosophers and physicists alike ponder whether time itself is a construct arising from our perception, an emergent feature of the universe's informational structure. Julian Barber, for example, argues that time is an illusion, a sequence of nows without an underlying temporal dimension. Yet, even if time is emergent or illusory at the quantum level, it remains undeniable in our lived experience and the macroscopic world. The tension between timeless fundamental laws and our temporal reality remains a central mystery. Beyond quantum physics, time plays a critical role in the biological world. Organisms are finely attuned to temporal cycles, from the circadian rhythms that regulate sleep and wakefulness to the seasonal migrations of animals. These biological clocks rely on molecular mechanisms that keep time with remarkable precision. In humans, the perception of time is linked to neural processes that integrate sensory information and memory. Our brains construct the flow of time, weaving past experiences with present awareness and future anticipation into a coherent narrative. Disorders of time perception, whether due to brain injury or altered states of consciousness, reveal just how fragile and complex this construction is. Psychological studies show that our sense of time can expand or contract depending on emotional states, attention, and context. Moments of intense focus may seem to slow time, while boredom or fatigue can make hours drag on endlessly. These subjective experiences highlight that time is not only a physical dimension, but a deeply personal phenomenon. As we continue our journey, we will explore the arrow of time in thermodynamics, the universal tendency toward increasing disorder, and how it shapes the irreversible flow of events in our universe. We will also examine time in cosmology, from the origin of the universe to its potential fate. Time remains a mystery, a concept that intertwines science, philosophy, and human experience inextricably. Each discovery opens new questions, inviting us to look deeper into the fabric of reality. The arrow of time, a concept deeply ingrained in our experience, arises most clearly in thermodynamics, the branch of physics that studies heat, energy, and entropy. Unlike the fundamental laws of physics, which often treat time symmetrically, thermodynamics reveals a distinct directionality, a one-way street along which events unfold. Entropy, a measure of disorder or randomness in a system, tends to increase over time in an isolated system. This principle, known as the second law of thermodynamics, explains why processes such as mixing cream into coffee, the burning of wood, or the melting of ice happen irreversibly. We never observe these processes, spontaneously reversing. This unidirectional flow from order to disorder gives time its arrow in the physical world. From the moment the universe began with the Big Bang, entropy has been increasing. The early universe was remarkably ordered, a hot, dense state of low entropy. Over billions of years, as galaxies formed, stars ignited, and planets coalesced, entropy grew. This growth provides a thermodynamic arrow of time that aligns with our psychological and cosmological arrows, the direction in which we remember the past but not the future, and the expansion of the universe. But why did the universe start in such a low entropy state? This question puzzles physicists and cosmologists. Some propose that the initial conditions of the cosmos set the stage for the arrow of time, a boundary condition that determines the directionality we observe. Others speculate about the existence of multiverses or cyclical universes where time's arrow might reverse. Entropy's inexorable increase also impacts life and complexity. Living organisms appear as islands of decreasing entropy, maintaining order and structure by consuming energy from their environment. Metabolism, growth, and reproduction are all processes that locally decrease entropy at the expense of increasing entropy elsewhere, in line with thermodynamic laws. On a cosmic scale, the eventual fate of the universe may be a heat death, a state of maximum entropy where all energy is uniformly distributed and no thermodynamic free energy remains, to sustain processes that increase complexity or life. In such a future, time's arrow would persist, but meaningful change would cease. The intimate connection between time and entropy influences many phenomena, including the flow of information. Information theory, developed in the 20th century, parallels thermodynamics in quantifying uncertainty and order. It provides new insights into the nature of time, suggesting that the increase of entropy correlates with the growth of information entropy. This framework ties time's arrow to the flow of information from past to future, shaping not only physics, but also communication, computation, and biology. In addition to thermodynamics, the cosmological arrow of time traces the universe's expansion. Since the Big Bang, space itself has been stretching, galaxies moving farther apart driven by dark energy. This expansion sets a direction, a before and after on a cosmic scale. The interplay between thermodynamic and cosmological arrows and their alignment with our psychological experience of time suggests a deep unity between physical processes and consciousness. Exploring the cosmos reveals that time, while seemingly universal, is influenced by local conditions. In regions of extreme gravity or acceleration, such as near black holes or neutron stars, time behaves counterintuitively, slowing or distorting. These effects challenge our intuitive notions and hint at the profound complexity of temporal experience. Black holes, mysterious regions where gravity becomes so intense that not even light escapes, create extreme time dilation. To an external observer, time near a black hole appears to nearly stop. Yet inside the event horizon, classical concepts of time and space break down, merging into singularities where known physics fails. Theoretical physics attempts to describe these extremes with quantum gravity theories, hoping to unify the large-scale curvature of space-time with the quantum nature of particles. Such unification might reveal the fundamental structure of time itself, possibly resolving paradoxes like the information loss problem in black holes. Our journey through time also intersects with cosmology's grandest questions, the universe's origin and fate. The Big Bang Theory describes a beginning of space and time, a singular event beyond which classical physics cannot describe what came before. Whether time existed before the Big Bang is a profound mystery. Some theories propose that time is cyclical or emergent from deeper timeless states, suggesting that what we perceive as time may be a phase in a grand cosmic cycle. The flow of time, its directionality, and its ultimate nature remain frontiers of inquiry, blending scientific discovery with philosophical reflection. As we proceed, we will explore how time shapes human experience, culture, and meaning, reflecting its central role in our understanding of existence. Time, while a fundamental dimension in physics, is also the canvas upon which human experience, culture, and meaning are painted. Our lives unfold in time's embrace, birth, growth, memory, and mortality, all rooted in temporal flow. This intimate connection between time and human consciousness has inspired philosophy, art, and science for millennia. From the earliest civilizations, humans have sought to measure and master time. Ancient cultures observed celestial cycles, the movements of the sun, moon, and stars, to develop calendars and timekeeping devices. These inventions allowed societies to coordinate agricultural activities, religious festivals, and social rituals, embedding time deeply into culture. The invention of mechanical clocks in the Middle Ages revolutionized human life, segmenting the day into discrete measurable units. This mechanization of time shaped modern society's rhythms, from work schedules to transportation timetables, creating an increasingly precise temporal order. Yet beyond measurement, time permeates language, memory, and identity. Our memories link past events, shaping who we are. Anticipation projects us into the future, fueling goals and hopes. This temporal structure forms the narrative of self, a continuous thread weaving together disparate moments into a coherent story. Philosophers have long debated whether time is real or an illusion. The ancient Greek philosopher Heraclitus asserted that everything flows, emphasizing change as the essence of reality. Conversely, Parmenides argued that change and time are illusions, and reality is eternal and unchanging. Immanuel Kant proposed that time is a form of human intuition, a framework our minds impose to organize sensory experience. Time, in this view, is not an external entity, but a condition of perception. More recently, thinkers like Henri Bergson distinguished between mechanical time, measured objectively by clocks, and lived time, the subjective flow of consciousness. This distinction reflects the dual nature of time as both a physical and psychological phenomenon. Our perception of time is fluid, elastic. Moments of joy can seem fleeting, while suffering can stretch endlessly. Studies show that time perception varies with age, emotional state, and attention. Children often experience time as slow and vast. Adults frequently feel it accelerating. The arts capture these nuances beautifully. Literature, music, and cinema explore temporal themes, memory's fragility, the tension between past and future, the fleeting present. Marcel Proust's monumental work, In Search of Lost Time, meditates on memory's power to transcend chronological time. In science fiction, time travel and alternate timelines provoke imagination and philosophical inquiry. Could we move backward or sideways in time? While current physics allows for some theoretical possibilities, practical time travel remains beyond reach. The relationship between time and free will also occupy philosophers and scientists. If the future is predetermined by physical laws, is choice an illusion? Quantum mechanics introduces indeterminacy, suggesting that uncertainty at fundamental levels might allow for genuine choice. Neurological research into how the brain constructs temporal experience reveals a complex orchestration of neural networks processing sensory input, memory, and prediction. Our sense of the now emerges from these processes, anchoring us in the ever-moving present. Moreover, technology reshapes our experience of time. The Internet's immediacy compresses temporal boundaries, connecting distant events instantaneously. Social media's constant updates fragment attention, altering how we perceive duration and continuity. At the same time, the increasing pace of life creates a paradox. Despite faster communication and travel, many report feeling rushed, pressed by time constraints. Mindfulness and meditation practices aim to counter this by cultivating present-moment awareness, slowing subjective time, and enhancing well-being. In the cosmic scale, human time is but a flicker, a brief pulse against the vast temporal ocean of the universe's lifespan. Yet within this brief span, time grants us consciousness, memory, and the ability to shape the future. The mysteries of time, its origins, flow, and meaning continue to inspire exploration across disciplines. It binds physics with philosophy, science with art, the infinite with the intimate. Our journey will continue, uncovering more layers of this profound dimension that frames our existence. Delving deeper into the fabric of time, we encounter its inseparable relationship with space, forming the four-dimensional continuum known as space-time. Einstein's theory of relativity revolutionized our understanding by merging these two seemingly distinct entities into a unified whole, profoundly changing how we perceive reality. In classical physics, space and time were absolute and independent. Time flowed uniformly everywhere, and space was a static stage where events unfolded. However, relativity reveals that both space and time are dynamic and relative, interwoven in a malleable fabric influenced by mass and energy. Special relativity introduced the concept that time is relative to the observer's motion. Moving clocks tick slower relative to stationary ones, a phenomenon called time dilation. This effect, negligible at everyday speeds, becomes pronounced at velocities approaching the speed of light. Consequently, two observers moving relative to each other may disagree on the duration of events. This insight shatters the notion of universal time, suggesting instead a multiplicity of times depending on the observer's frame of reference. Moreover, simultaneity, the idea that two events occur at the same time, is also relative. What is simultaneous for one observer may not be for another, challenging our intuitive grasp of temporal order. General relativity extends these ideas by describing gravity as the curvature of space-time caused by mass and energy. Massive bodies like planets and stars warp space-time, affecting the passage of time. Near a massive object, time runs slower relative to a distant observer, an effect called gravitational time dilation. This phenomenon has practical consequences, for instance, in the operation of GPS satellites, which must account for both special and general relativistic time dilation to provide accurate positioning data. The fabric of space-time is not a passive backdrop but an active participant in the cosmos's evolution. Gravitational waves, ripples in space-time caused by cataclysmic events such as colliding black holes, demonstrate this dynamic nature. Detected only recently, These waves offer new windows into the universe and its temporal processes. Relativity also intertwines time with causality, the principle that causes precede effects. The speed of light sets a cosmic speed limit, ensuring causal order. No information or influence can travel faster than light, preserving temporal sequence and the logical structure of events. Yet, theoretical constructs like wormholes or closed time-like curves suggest possibilities of time loops, where cause and effect could become entangled in paradoxical ways. These concepts fuel speculative ideas about time travel, but remain unresolved. Within current physics, the interrelation of space and time challenges us to reconsider fundamental questions. Is time a dimension like space, or is its passage fundamentally different? Does the flow of time arise from the geometry of space-time, or from thermodynamic or quantum processes? Moreover, the geometry of space-time underlies the universe's large-scale structure. Cosmological observations reveal that the universe is expanding, its geometry influenced by matter, and dark energy. This expansion defines a temporal framework, a cosmic clock ticking from the Big Bang to the distant future. The beginning of time itself, the moment of the Big Bang, raises profound mysteries. Was there a before? Did time emerge with space? Or does it extend beyond our observable universe? These questions border on the limits of empirical science and enter the realm of metaphysics. Contemporary theories propose that space-time may be emergent, arising from more fundamental pre-geometric entities. Concepts such as holography and the AD-SO-CFT correspondence suggest that a lower dimensional boundary encodes the information of our higher dimensional universe, implying that space-time, and therefore time, might be a derived phenomenon. Furthermore, the arrow of time in relativistic contexts remains an active area of investigation. While relativity's equations are time-symmetric, the observed directionality of time correlates with boundary conditions and thermodynamic considerations. The merging of relativity and quantum mechanics, the two pillars of modern physics, is essential for a complete understanding of time. Quantum field theory incorporates relativistic principles, but still grapples with conceptual and technical challenges. Efforts to develop a quantum theory of gravity, whether through string theory, loop quantum gravity, or other frameworks, aim to reveal the true nature of space-time and time itself, potentially unveiling a new paradigm where time may lose its classical meaning. In our daily lives, these cosmic and quantum insights remain mostly hidden, yet they inform technologies, shape our worldview, and deepen our sense of wonder. As we continue, we will explore how time influences phenomena from the microscopic to the cosmic, revealing a dimension rich with complexity and mystery, integral to everything that exists. At the smallest scales of existence, time takes on a more enigmatic character, interwoven with the quantum fabric of reality. Quantum mechanics, the science of the subatomic world, paints a picture of nature where uncertainty, probability, and superposition reign. In this domain, time no longer behaves as the smooth, continuous flow familiar to classical physics. One of the most striking aspects of quantum mechanics is its probabilistic nature. Particles do not possess definite positions or velocities until measured. Instead, they exist in a haze of possibilities, described by a mathematical construct called the wave function. This wave function evolves smoothly and deterministically according to the Schrödinger equation, yet upon observation, it appears to collapse into a definite outcome. Time in this framework seems to have a dual role. On one hand, it appears as an external parameter that drives the evolution of the wave function. On the other, during measurement, when probability becomes reality, time seems to act discontinuously, marked by abrupt changes and outcomes. This dichotomy challenges the classical notion of time as a seamless continuum. The famous quantum measurement problem illustrates this tension. If the wave function's evolution is governed by precise laws, what causes it to collapse upon observation? Where and when exactly does this collapse occur in time? Various interpretations of quantum mechanics, such as the Copenhagen interpretation, the many worlds interpretation, and objective collapse theories, offer differing answers, but none have resolved the issue definitively. The question deepens when we consider entanglement, a phenomenon where particles become correlated such that the state of one instantly influences the state of another, regardless of the distance between them. This spooky action at a distance, as Einstein called it, seems to defy the classical notion of causality and time ordering. If measuring one particle instantaneously affects another, what does that imply about the temporal structure of the universe? Some physicists argue that time, as we perceive it, may not be fundamental at all, but rather an emergent property arising from deeper atemporal quantum laws. One theoretical proposal attempting to reconcile quantum mechanics and time is the Page-Wooter's mechanism, which suggests that time emerges from entanglement itself. In this view, the universe as a whole exists in a timeless quantum state, but for observers embedded within it, time appears to flow due to correlations between subsystems. That is, time is not absolute, but relational, an emergent phenomenon, depending on the observer's entanglement with their surroundings. This idea aligns with certain interpretations of quantum gravity, where time might disappear altogether. In canonical quantum gravity, the Wheeler-DeWitt equation, analogous to the Schrödinger equation for the entire universe, contains no time variable at all. The universe appears frozen, suggesting that the apparent flow of time arises from the internal structure of the system, rather than from any external ticking clock. Loop quantum gravity, another contender for a theory of quantum spacetime, proposes that space and time are quantized, that is, they consist of discrete units. In this granular view, time may be a sequence of quantum events rather than a continuous river. Just as matter is made of atoms, time might be composed of indivisible moments. These quantum perspectives offer radical reconceptualizations of time, far removed from our everyday experience. Yet, they may be essential to resolving the deep inconsistencies between general relativity and quantum mechanics. Even more intriguingly, experiments are now probing these frontiers. In quantum computing, where entangled particles are manipulated to perform complex calculations, the role of time becomes subtle. Quantum circuits operate not just sequentially, but also in ways where temporal order is superposed, leading to new concepts like indefinite causal order. Such experiments hint that at the quantum level, time might not only be flexible, but also structurally different from classical intuitions. Events may not happen in a fixed sequence, but in a superposition of possible orders, where cause and effect blur. Moreover, efforts in quantum cosmology attempt to understand how the universe's earliest moments, before classical space-time emerged, were governed by purely quantum laws. These models suggest that time as we know it may have crystallized from a timeless quantum reality, emerging only when the universe reached a certain scale or complexity. The implications of these ideas extend beyond physics. If time is not fundamental, what does that mean for our understanding of memory, consciousness, and identity? Are our lives unfolding along a fixed script in the quantum fabric, or are we co-creating the future with every observation and interaction? As we continue to explore these questions, we find ourselves not merely studying time, but participating in it. Each thought, each moment, a ripple in the quantum field, a mark in the unfolding tapestry of existence. Let us now continue, delving deeper into the arrow of time and the inexorable flow from past to future, a direction so familiar, yet so mysterious. The arrow of time, our perception that time flows from the past through the present toward the future, is one of the most deeply felt aspects of human experience. We remember the past, but not the future. We can influence what is yet to come, but not what has already been. Yet from the standpoint of physics, especially in the realm of fundamental laws, the direction of time is curiously absent. The equations that govern microscopic processes are largely time-symmetric, They work equally well if time flows forward or in reverse. So why then do we experience a distinct direction, a one-way street that never allows us to return? The key to understanding this asymmetry lies not in the laws themselves, but in the conditions under which they operate. This is where the second law of thermodynamics enters the story. According to this law, the entropy of an isolated system, its degree of disorder, tends to increase over time. Entropy defines the arrow. It is why we see ice cubes melt, but never spontaneously form. Why a house may collapse into rubble, but rubble never assembles itself into a house. In a universe governed by probability, order gives way to disorder simply because disorder is statistically more likely. This thermodynamic arrow of time aligns with our lived experience. From the Big Bang, a low entropy, highly ordered state, the universe has been evolving toward greater entropy. Stars burn their nuclear fuel, galaxies drift apart, and the very fabric of cosmic structure dilutes over aeons. As entropy increases, so does the irreversibility of processes. It is this statistical tendency that gives us our sense of temporal flow. Yet the second law raises an even deeper question. Why did the universe begin in such a low entropy state? This is one of the great puzzles of modern cosmology. If high entropy states are more probable, why was the early universe so improbably ordered? One possibility is that it simply was, an unexplained initial condition. Another is that there exist deeper, perhaps unknown laws or boundary conditions that necessitate such an origin. Another arrow closely tied to entropy is the psychological arrow of time, the subjective sense of past, present, and future. Neuroscience tells us that memory and anticipation are central to this experience. We encode information about events that have happened, but cannot access events yet to come. This asymmetry mirrors the thermodynamic arrow, suggesting that our cognition is built atop the physical foundations of entropy and causality. We also find a radiative arrow of time in the way waves, whether sound, light, or gravity, propagate outward from a source. A stone thrown into a pond creates ripples that travel away, never toward the stone's hand. This directional behavior, though allowed by time-symmetric equations, follows the entropic gradient and thereby reinforces our sense of forward flow. On larger scales, the cosmological arrow of time is tied to the universe's expansion. As space itself stretches, time seems to move forward with it. Some theories suggest that if the universe were to eventually contract, the arrow could reverse, though such speculation remains unconfirmed and deeply controversial. In quantum mechanics, as previously explored, the situation becomes even murkier. Though the underlying dynamics are time-reversible, the act of measurement appears to break this symmetry. The collapse of the wave function introduces an apparent temporal direction. Before the measurement, many possibilities. After it, one reality. Whether this collapse is real or just apparent is a matter of interpretation, but its implications for time are profound. Furthermore, research in quantum thermodynamics, an emerging field, suggests that entropy and irreversibility can also arise from entanglement and quantum information theory. Systems gain entropy not just from disorder, but from how information is distributed and hidden across subsystems. In the interplay between entropy, information, and observation, we begin to see a richer tapestry for the arrow of time. Yet there are paradoxes. In certain interpretations of physics, all moments in time exist equally, past, present, and future, just like all locations in space. This block universe view suggests that time doesn't really flow, but that our perception of motion through time is an illusion born of consciousness. In this view, the arrow is not a fundamental feature of reality, but a projection of our internal processing. This idea challenges the very notion of becoming. If the future is as fixed as the past, then free will, causality, and moral responsibility come under philosophical scrutiny. Do we carve the future with our choices, or merely move through a pre-written script? Some physicists resist the block universe on these grounds, favoring instead becoming theories, in which time is dynamic and events come into existence. These models seek to rescue the flow of time by positing that the present is ontologically special, more real than the past or future. Though elegant in motivation, these theories face technical hurdles in reconciling with relativity and quantum theory. Perhaps the resolution lies in recognizing that our theories are models, approximations of deeper truths not yet grasped. Time may be emergent, relative, and directionless in its foundations, yet appear to flow in the macro world due to statistical, informational, and experiential reasons. The arrow of time, then, is not an illusion, but a manifestation, an emergent property of the way the universe organizes information, spreads energy, and evolves complexity. It is the consequence of a cosmos that began in extraordinary simplicity and has been unfolding into ever greater intricacy. In the next section, we shall step even further into the mystery by exploring how time governs biological life, how living organisms perceive, respond to, and are shaped by temporal rhythms. From the heartbeat to the lifespan, time courses through every cell, every breath. Time in biology is not just a passive backdrop, it pulses through every organism, shaping growth, decay, memory, reproduction, and behavior. From the moment life begins, it is caught in an intricate dance with time, measured not in hours or seconds, but in cycles, rhythms, and irreversible transitions. Cells divide, hearts beat, bodies age. Life tells time not with clocks, but with patterns that echo the turning of planets, the rising of suns, the falling of leaves. At the core of biological time lies the circadian rhythm, a roughly 24-hour cycle found in virtually all forms of life, from simple cyanobacteria to complex human beings. This rhythm is not learned but encoded. Deep within our cells, clusters of genes and proteins interact in feedback loops that oscillate with astonishing regularity. These molecular clocks govern when we sleep, wake, digest food, release hormones, repair tissues, and perform countless other vital functions. Light is the primary signal that synchronizes our internal clocks with the external world. Special. Photoreceptor cells in the retina detect changes in ambient light and transmit this information to the suprachiasmatic nucleus, a small region in the brain's hypothalamus. This master clock adjusts our physiological rhythms to align with the solar cycle, ensuring that our bodies anticipate the day and night before they arrive. But this alignment is not perfect. Shift work, jet lag, and screen exposure can disrupt circadian timing, leading to a cascade of biological dysfunctions, sleep disorders, metabolic imbalance, immune suppression, even increased risk of disease. When time in the body falls out of sync with time in the environment, life suffers. We are, it seems, not just creatures of time, but finely tuned instruments calibrated to its flow. Biological time is not limited to daily cycles. Seasonal rhythms also shape life on Earth. Migration, hibernation, flowering, mating. These behaviors unfold in sync with longer temporal patterns driven by changes in daylight, temperature, and food availability. The timing must be precise. A bird that migrates too early may find no food. A flower that blooms too late may miss its pollinators. Survival depends on temporal intelligence, a capacity honed by evolution to anticipate the future based on the past. On a more intimate scale, time lives in the heartbeat. The average heart beats 100,000 times per day, its rhythm both mechanical and adaptive. It speeds up with exertion, slows down with rest, and synchronizes with respiration, emotion, and even the presence of another person. This rhythm is more than a pump. It is a biological metronome that marks the passage of each moment with silent precision. The tempo of life varies across species. A hummingbird's heart may beat 200 times per minute. A whale's, just a few dozen. Lifespans correlate loosely with metabolism. Fast lives tend to be short. Slow lives stretch longer. This scaling of time with biology suggests that each organism experiences the flow of time differently. A fly may live only days, but those days may be rich with temporal complexity. where a moment for us feels like an hour for them. Then there is developmental time, the process by which a single fertilized cell becomes a complex organism. This unfolding is staggered, sequenced, and choreographed in minute detail. Genes switch on and off in ordered cascades. Limbs elongate. Organs mature. Brains wire themselves to the world. Every phase is timed to perfection. A delay of hours in early embryonic development can result in profound consequences. Life unfolds not only in space, but in precisely calibrated durations. Memory, too, is a function of biological time. Our ability to store, retrieve, and anticipate is anchored in the hippocampus and cerebral cortex, where networks of neurons encode sequences of events. Memories are not static snapshots, but dynamic reconstructions shaped by emotion, repetition, and relevance. We remember time not as it was, but as it mattered. Emotional events feel longer. Repetition shortens perception. A childhood summer seems endless. An adult year slips by unnoticed. Even our sense of the present, the elusive now, is shaped by biology. Studies suggest that the brain constructs a rolling window of temporal integration, about 2 to 3 seconds long, within which sensory events are perceived as simultaneous. Outside this window, events are seen as occurring before or after each other. Thus, the present is not a point but a bubble, a subjective blend of recent past and imminent future that allows us to perceive continuity, causality, and motion. On longer timescales, the biological clock measures age. Telomeres, protective caps at the ends of chromosomes, shorten with each cell division, eventually triggering cellular senescence. Mitochondria accumulate damage. Proteins misfold. Systems lose efficiency. Aging is not a uniform process, but a gradual erosion of temporal harmony across systems. Death, when it comes, is not an event, but a culmination, a slowing of rhythms, a cessation of synchrony, the final punctuation in the biological script of time. Yet in some creatures, time behaves strangely. The axolotl retains juvenile features throughout its life, defying the usual developmental clock. Tardigrades can enter a cryptobiotic state, suspending biological time for years, even decades, until conditions improve. These examples hint that time in biology is not fixed but flexible, a variable that life can stretch, compress, or pause. Research into aging and longevity seeks to understand this flexibility. Scientists are uncovering genetic pathways, molecular switches, and environmental factors that influence biological time. Caloric restriction, certain compounds, and even alterations in circadian rhythm can extend lifespan in model organisms. One day, we may learn to modulate time itself, not by changing its flow, but by changing our body's response to it. In all of this, we see that time in biology is both internal and external. It is lived, measured, and shaped by the body's own rhythms, yet constantly influenced by the larger temporal architecture of Earth and cosmos. Life is not a passenger in time. It is a timekeeper, a composer of rhythms nested within rhythms. As we move forward, the question deepens. If life perceives and constructs time through rhythm and memory, could consciousness itself be the ultimate clock? In the next part, we explore the mind's role in shaping the flow of time, how attention, emotion, and awareness distort, expand, and compress our experience of the present moment. Consciousness, in all its elusive complexity, does not merely exist in time, it sculpts it. In the theater of the mind, time becomes pliable, stretched by joy, compressed by routine, suspended by awe, and fragmented by trauma. Where physics defines time with equations and thermodynamics, the brain experiences it with sensation, emotion, and memory. The inner clock of consciousness beats to its own rhythm, often at odds with objective measures. In this part, we journey into how the mind perceives, distorts, and even creates the flow of time. Think first of attention, the beam of awareness that filters our experience. Neuroscience reveals that when we attend closely to our environment, time feels slower. This is not because external time has changed, but because we are encoding more information per unit of experience. A sudden event like a car accident or a near fall seems to unfold in slow motion. This phenomenon, known as time dilation in psychology, arises from our brain's heightened processing and memory storage under stress or novelty. We are not observing more time. We are noticing more of what occurs within it. Conversely, routine dulls time. Days filled with repetition, commutes, meetings, chores, blur into a single undifferentiated stretch. Looking back, they occupy little space in memory. A week seems to vanish. But an eventful vacation, filled with unfamiliar sights, languages, and interactions, expands in retrospect. The richness of memory leaves behind temporal footprints. This is why time feels fast as we age, not because the seconds are shorter, but because the mind registers fewer new patterns, fewer surprises, less detail, less perceived time. Emotion is another powerful time sculptor. Fear and anticipation stretch moments into eternities. Boredom expands minutes into hours. Meanwhile, love, laughter, and flow, the total immersion in an activity, collapse time altogether. Hours pass in what feels like minutes. These states share a neurochemical fingerprint. Dopamine, serotonin, and endorphins alter perception, shifting the gears of our internal chronometer. Time, in these moments, obeys no master but the mind. Dreams represent perhaps the most mysterious distortion of time. Within seconds of REM sleep, the brain weaves elaborate stories, sequences, and sensations that seem to span hours. Yet when measured, these dreams unfold in real time. How can so much happen in so little? One theory suggests that the dreaming brain skips the narrative steps we normally require while awake. It stitches symbols together without logic or continuity, giving the impression of vast duration in compressed intervals. Time in dreams is not linear, but emotional, symbolic, unconstrained by causality. Meditation and altered states of consciousness offer further windows into subjective time. In deep meditation, practitioners often report the dissolution of time altogether, a timeless now, where thoughts, sensations, and the self itself recede. Neuroscientific studies show that these states correlate with decreased activity in the brain's default mode network, a system linked to self-referential thinking. When the self fades, so too does its temporal anchor. Without a narrative, there is no past, no future, only presence. Psychedelic experiences can produce similar effects. Substances like LSD or psilocybin alter the connectivity between brain regions, loosening the rigid sequence of ordinary time perception. Users report time loops, eternity, or moments that feel frozen. These distortions hint at the brain's flexibility, its capacity to generate multiple timelines, or to collapse them into a singular experience beyond time. The psychology of time extends to memory, our inner archive of temporal experience. But memory is not a perfect recording. It is a reconstruction, filtered by emotion, purpose, and identity. We do not remember time. We remember events in time. And each time we recall them, we alter them. Neuroscientists call this reconsolidation. Memory, then, is not the past itself, but a living narrative, updated with each retrieval. It is how the mind recreates time from fragments. Future thinking, or prospection, is built from the same neural architecture as memory. The hippocampus, medial prefrontal cortex, and other regions involved in remembering also activate when we imagine future scenarios. We construct time forward the same way we reconstruct it backward. The difference lies not in the data, but in the direction. We live in anticipation as much as we live in recollection. Cultural perspectives further shape time perception. In some languages, time flows from left to right, in others, from east to west, or even top to bottom. Some cultures view the future as behind them, unseen and unknown, while the past lies ahead, visible and remembered. These metaphors are not trivial. They influence how people plan, reflect, and make decisions. Western culture emphasizes clock time, quantifiable, scheduled, efficient. Indigenous cultures may prioritize event time, where actions begin when conditions are right, not when the clock demands. The mind, molded by culture, learns to move through time differently. In daily life, technology further compresses and fragments our temporal experience. Notifications, instant messages, streaming media, all erode the continuity of attention. We live in split seconds, constantly switching contexts, rarely inhabiting a moment fully. Some researchers call this present shock, the disorientation caused by too much now. Paradoxically, though we have more control over time than ever before, we often feel we have less of it. We are drowning in time, yet starving for presence. This fragmentation impacts not only perception, but mental health. Anxiety often arises from a fixation on the future, depression from a rumination on the past. Healing, in many therapeutic approaches, involves reorienting the patient in time, anchoring them to the present, revisiting the past with new insight, and reshaping the future with hope. Time, in the mind, is not neutral. It is deeply emotional. Children perceive time differently still. With fewer memories and less expectation, their now is expansive. A day can feel endless. Waiting for a birthday or holiday seems unbearable. As we grow, the accumulation of experience compresses time. The brain no longer needs to process every detail. It predicts, abbreviates, streamlines. Time speeds up not because it accelerates, but because we notice less of it. In the end, subjective time is not an illusion, but a construction, no less real for being internal. Just as the eye shapes color and the ear shapes sound, the brain shapes time. It bends around emotion, twists under memory, expands with awe, and collapses in routine. We are not merely in time, we are its architects. In the next part, we move from perception back to cosmos. If time can be bent by gravity, experienced differently by consciousness and constructed by life, then what is its ultimate nature? Is time fundamental or emergent? Is it real or a relational shadow of deeper truths? Let us turn to the edge of physics and philosophy, where space-time trembles and timelessness beckons. The search for the ultimate nature of time leads us to the edges of human understanding, where physics begins to blur into metaphysics and science folds into speculation. Here, we encounter profound questions that defy easy resolution. Is time a fundamental component of the universe, or does it emerge from something deeper? Could the flow of time itself be an illusion? What happens to time at the smallest scales of reality, or at the very beginning of everything? In this part, we venture into the conceptual frontiers where cosmology, quantum theory, and the philosophy of physics converge to ask, what is time, really? At the heart of these questions lies a contradiction. On one hand, in everyday life and classical physics, time is linear and absolute. It ticks forward with dependable consistency, allowing for causality, memory, and motion. On the other hand, at the extremes near black holes during the birth of the universe, or within the equations of quantum gravity, time begins to dissolve or behave in unexpected ways. This tension between our experience and our theories suggests that time may not be what it seems. One major step in this realization came with Einstein's general theory of relativity. As we've seen, time is not separate from space, but part of a unified space-time fabric. Gravity, as described by Einstein, is not a force acting at a distance but a curvature in space-time caused by mass and energy. This means that what we perceive as the passage of time is actually the geometry of the universe shifting in response to its contents. And as we also know, this leads to time dilation, clocks ticking at different rates depending on gravity and motion. But general relativity has no preferred now. Its equations are timeless in a curious way. They describe relationships between events, not their unfolding through time. There is no cosmic second hand, no universal present slicing through the block of spacetime. Every point in the four-dimensional spacetime block simply exists. From this perspective, past, present, and future are equally real, an idea known as the block universe. This notion undermines our intuitive understanding of time's flow. If all moments exist equally, then the passage of time might be a feature of consciousness, not the universe. It might be that we do not move through time, but rather our awareness moves through slices of space-time, giving the illusion of flow. This concept aligns with what some physicists call eternalism, the idea that the universe is a static 4D structure, and time is simply a dimension we experience one moment at a time. Contrast this with presentism, the belief that only the present is real, that the past has ceased to be, and the future has yet to exist. Presentism aligns with human experience, but not with relativity, which makes no distinction between past, present, and future. These philosophical disagreements point to a deeper problem. Our theories do not agree on the role of time. Enter quantum mechanics. In the quantum realm, where particles behave both like waves and points, and where probability governs outcomes, time still appears in equations, but its role is strange. The Schrödinger equation, central to quantum mechanics, describes how a system's wave function evolves over time. Yet, unlike in relativity, time here is absolute and external, like Newton imagined. It's a background parameter, not part of the system being described. This inconsistency has haunted physicists for decades. How can time be flexible and relational in relativity, yet fixed and external in quantum theory? To reconcile the two, we need a theory of quantum gravity, a unified framework that merges quantum mechanics with general relativity. And this is where time becomes even stranger. In attempts at quantum gravity, such as loop quantum gravity and string theory, time often disappears from the equations altogether. For example, in the Wheeler-DeWitt equation, an equation proposed as a candidate for the wave function of the universe, there is no time variable at all. The universe, it seems, just is. In such formulations, the universe is described by a timeless state, and time emerges only when we consider subsystems or observe change. This has led to the idea that time is not fundamental, but emergent, like temperature, which arises from the motion of countless particles, or pressure, which is the statistical result of microscopic collisions. Time may arise from more primitive, timeless ingredients. It may be that what we call time is the result of entanglement, decoherence, or the thermodynamic flow of information. One promising approach to this idea is the Page and Wooters mechanism, which proposes that time can emerge in a quantum system from entanglement. In this view, the universe as a whole exists in a timeless quantum state. But if we partition it into a system and an observer, then from the observer's perspective, time appears to flow. Time is thus relational, not a thing in itself, but a way of describing the correlation between different parts of the universe. Another fascinating development comes from studies in quantum information theory. Researchers like Seth Lloyd and Carlo Rovelli suggest that time arises from the flow of information. In a universe governed by informational constraints, the direction of time may be a result of how data propagates and decoheres. Rovelli's relational quantum mechanics goes further, suggesting that physical properties, including time, only exist in relation to an observer. If time is emergent, then we must ask, emergent from what? Some physicists speculate that space-time itself may emerge from quantum entanglement. The ER-EPR conjecture, proposed by Leonard Susskind and Juan Maldacena, suggests a profound link between wormholes, Einstein-Rosen bridges, and quantum entanglement. In this view, space-time geometry is not fundamental, but woven from the threads of quantum information. Time, as a component of space-time, would then be a byproduct of entangled correlations. These ideas are breathtaking and speculative. We do not yet have the tools or experiments to verify them, but they point toward a radical reimagining of the universe. If time is not fundamental, then the beginning of time, the Big Bang, might also be an illusion. Some models of the universe, such as eternal inflation or cyclic cosmologies, posit no true beginning, only transitions between states. Others suggest that before time there was a timeless quantum foam from which space-time crystallized. So where does this leave us? Time, in this frontier of physics, is a mystery greater than ever. It may not exist at the deepest level of reality, or it may be more real than anything else, a measure not just of change, but of being. It may arise from entropy, emerge from information, or result from consciousness itself. It may be a shadow of something we cannot yet grasp. Yet despite its elusive nature, time remains our most intimate companion. It is the rhythm of our breath, the arc of a falling leaf, the aging of stars and the unfolding of thought. It is both the canvas and the brushstroke, the stage and the motion. And even if we one day find that time is an illusion, it will have been a beautiful one. In the next part, we will explore time's role in the ultimate fate of the universe. If time has a beginning, does it also have an end? How will the cosmos evolve across billions of years? What is the destiny of time in a universe of dark energy, entropy, and silence? As we journey deeper into the mystery of time, we inevitably come to face its destiny. If time had a beginning, as suggested by the Big Bang, does it also have an And what is the fate of time itself in a universe that continues to expand, cool, and age? In this part, we cast our eyes toward the future, not just the future of human life or of Earth, but the far, far future of the cosmos. We ask not only, what will happen to time, but what role time will play as the universe moves toward its final chapters, and whether time itself might fade away. Our story begins with the concept of cosmic evolution. From the Big Bang, a fiery, dense singularity, the universe has expanded for roughly 13.8 billion years. Galaxies formed, stars were born and died, and heavier elements emerged in the hearts of supernovae. Time, as we measure it, has marched forward, marked by events, transitions, and irreversible processes. But this forward march is not necessarily eternal in the way we commonly imagine. To understand the future of time, we must first examine the drivers of cosmic change. The most fundamental of these is entropy, the second law of thermodynamics, which states that the total entropy of an isolated system can only increase. In simpler terms, disorder always grows. Stars burn their fuel, systems break down, and eventually, energy spreads so evenly that no more work can be extracted. This principle is central to the concept of the arrow of time, the idea that time has a direction, from past to future, because of the flow of entropy. This arrow gives time its asymmetry. We remember the past, not the future. We age, not grow younger. A dropped glass shatters but never reassembles itself. All of this, from a physical standpoint, is because the universe began in a highly ordered state and has been moving toward greater disorder ever since. But what happens when the disorder becomes complete? When there are no more gradients, no more energy flows, no more differences between one region and another? This leads us to one possible endgame scenario for the universe: heat death, also known as the Big Freeze. This is the idea that the universe will continue expanding forever. Galaxies will drift apart, stars will burn out, and black holes will slowly evaporate through Hawking radiation. Eventually, all matter will decay into subatomic particles, and the universe will become a cold, dark sea of photons and low-energy particles. No events, no motion, no change. In such a state, time as we experience it may cease to have meaning. With no events to mark its passage, time may still mathematically exist, but it will be empty, silent, still. There are other scenarios. The Big Rip posits that the universe's expansion will accelerate due to dark energy until it tears apart galaxies, stars, atoms, and finally space-time itself. In this vision, time ends in violence. In contrast, the Big Crunch suggests a reversal. If the density of the universe were high enough, expansion could stop and reverse, collapsing everything back into a singularity. Time, in this model, would run toward another beginning, perhaps leading to a new universe, a new cycle. More speculative still are ideas from quantum cosmology. Some suggest that time may be cyclic. The universe expands, contracts, and rebounds in an endless loop. In each cycle, time resets, perhaps with new physical constants, new laws. In these models, time may not have a beginning or an end, but an eternal rhythm. This concept finds echoes in ancient philosophies and mythologies, which often imagined time as a wheel or circle, endlessly turning. But in the modern physical sense, we must return to entropy. Even if the universe cycles, entropy must somehow reset between cycles. Otherwise, each cycle would begin with higher disorder until the cycles become meaningless. Some theoretical frameworks try to solve this, such as conformal cyclic cosmology proposed by Roger Penrose, which posits that at extreme scales of expansion, the universe forgets its size, allowing time to restart in a new aeon. At the heart of all these ideas lies a question. Is time a feature of the universe that will persist forever? Or is it something that could end, gradually or suddenly? If time is emergent, arising from entropy, motion, and interaction, then the fading of these things may also signal the fading of time itself. Let us now consider black holes, not just as cosmic vacuum cleaners, but as time machines of a sort. Near a black hole's event horizon, time slows dramatically. For an outside observer, a clock falling into a black hole appears to freeze. What happens beyond the event horizon remains a mystery, but it raises fascinating questions about time's structure. Could time stop altogether inside a black hole? Or is time replaced by space, as some models suggest? The most intriguing twist comes from Stephen Hawking's proposal about imaginary time. In certain quantum gravity models, time becomes a fourth, spatial dimension at the beginning of the universe. Instead of a singular point of infinite density and temperature, the Big Bang becomes a smooth, rounded point in imaginary time, removing the need for a beginning in the usual sense. This idea implies that asking what came before the Big Bang may be like asking what's north of the North Pole, a question without meaning in that geometry. If this is true, it reframes our understanding of time's origin and its fate. Time may not have started at the Big Bang in a singular flash, but emerged gradually from a timeless quantum state. And if it emerged once, it might do so again. Or perhaps we are simply a fluctuation in a larger, timeless sea, a brief flicker of order before the return to cosmic silence. There is also the question of consciousness. Some theorists speculate that time might be intimately linked with the observer. Julian Barber, for instance, argues that time does not exist. Instead, the universe is a collection of nows, snapshots of configurations. Motion and change are illusions created by our minds, linking these snapshots in memory and perception. From this perspective, time is not a fundamental feature of the cosmos, but a psychological construct, a way we navigate the eternal landscape of reality. This idea loops us back to a recurring theme. That time, like beauty or color, might be something that emerges in the interaction between the universe and the mind. If the universe forgets how to change, if its entropy becomes maximal, its particles evenly distributed, then perhaps time, too, will dissolve, like a story ending when the last page is turned. But for now, we live in a universe where stars shine, planets spin, and hearts beat. Time still flows, and we, its temporary travelers, experience its passage with wonder, grief, anticipation, and awe. We mark it with birthdays and sunsets, with seasons and songs. We know it as a river we can neither halt nor reverse, only ride. And so we return to our place in this cosmic tale. Our lives are brief flickers against the backdrop of cosmic time. But within those flickers lie entire universes of thought, feeling, discovery, and connection. Time may not last forever, but while it lasts, it is ours. In the next part, we reflect on the poetic and philosophical implications of time's mystery. From ancient myths to modern physics, how have humans grappled with the meaning of time? What does it mean to live in time, to be aware of its passing, to remember, to hope, to dream? We step away from equations and theories to explore time as experience, as metaphor, as the heartbeat of existence. From the ticking of a clock to the shifting of shadows at dusk, time is not merely a scientific concept, it is a deeply human experience. While physics seeks to define time in equations and cosmic frameworks, human beings have always perceived time as a rhythm, a presence, a silent companion that shapes our days and gives structure to our lives. In this part, we explore the emotional, philosophical, and poetic dimensions of time. What does it mean to live within time, to be aware of its passing? How have different cultures and minds sought to capture its essence? Time touches everything we do. It governs our schedules, our memories, our hopes. It gives urgency to action and meaning to stillness. Every moment we live is steeped in it. Yet when we try to grasp what time truly is, beyond the calendar and the clock, it slips through our fingers like mist. We cannot hold it, pause it, or rewind it. We can only live in it one breath at a time. Poets have long been captivated by this paradox. Shakespeare wrote of time's whirligig of fate, and Emily Dickinson called it a subtle thief of youth. The ancient Greeks had multiple words for time: chronos for sequential measurable time, and kairos for the right or opportune moment. In many indigenous traditions, time is not a line but a cycle, a dance of repetition, of seasons and ancestors and renewal. And then there is memory. Memory is how we keep the past alive, how we measure the distance we've traveled. It is the canvas upon which time leaves its traces. Neuroscience tells us that memory is not a perfect recording, but a reconstruction. Each time we recall, we rebuild. Time, then, is not only in the ticking of seconds, but in the way we remember, in the stories we carry. Think of childhood. Those long, endless summers that seem to stretch forever. Yet now, in hindsight, they are condensed into flashes, moments, sensations, the sound of cicadas, the smell of wet grass, the soft glow of streetlights. As we age, time seems to accelerate, not because it changes, but because our perception of it does. A year to a child is a vast landscape. To an elder, it is a single step. Philosophers, too, have wrestled with time's mystery. St. Augustine confessed, "What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know." Heidegger saw time as the horizon for understanding being itself, arguing that to be human is to be temporal, to exist always in the tension between what was and what may be. In Eastern traditions, time is often seen less as a straight path and more as a flowing river, continuous, circular, and interconnected. The Tao Te Ching speaks of the way things unfold in their own time, harmoniously. In Buddhism, impermanence is a core truth. All things arise, exist briefly, and pass away. Clinging to permanence is suffering. Letting go allows peace. Time, then, is not the enemy, it is the teacher. In literature, time is often the stage upon which love and loss play their parts. Marcel Proust's masterpiece, In Search of Lost Time, is a vast meditation on memory and the way time shapes identity. In Virginia Woolf's To the Lighthouse, the passage of time is not linear, but textured, bending and folding around human consciousness. Time in these stories is not a background element, it is the very substance of the narrative, as essential as character or plot. Music, too, is built on time. Rhythm, tempo, silence, all depend on the structuring of time into form. A melody is time made audible. A symphony is time organized into emotion. And when we listen, we step into its flow, surrendering to its rise and fall. But time is not only external, it lives within us. Our bodies are clocks of many kinds. Our hearts beat rhythmically. Our cells divide in cycles. Our hormones follow circadian rhythms. Sleep and wakefulness, hunger and satiety, even mood and alertness, all dance to the rhythms of internal timekeepers. And when those rhythms falter, we feel it deeply: jet lag, insomnia, disorientation. In moments of intense emotion, time changes. Texture. Joy can make hours vanish in a flash. Grief can make seconds stretch into eternity. Waiting dilates time. Urgency compresses it. A kiss, a goodbye, a moment of awe. These are not measured by the clock, but by the depth of experience. Time also gives us meaning through anticipation and reflection. The ability to imagine the future allows us to plan, to hope, to strive. The ability to remember lets us learn, connect, grieve. Without time, there is no story, no growth, no history. We live not just in the present, but in the arc that connects what has been to what might be. And yet for all its intimacy, time remains alien, elusive. It flows without pause, indifferent to our longings. It can heal, but it can also wound. It gives and takes in equal measure. We may curse it, plead with it, try to outrun it, but we cannot escape it. Still, we try. We mark it with calendars, stretch it with routines, preserve it in photographs, defy it with science. But always, it moves on. There's a quiet beauty in accepting this. To know that everything is temporary is to cherish it more. Each sunrise is unique. Each goodbye, final. Each breath, a gift. To live fully is to embrace time, not as a foe, but as a companion. Not as a line to race across, but as a canvas to paint with presence. In the next part, we explore how time interacts with technology, and how our attempts to measure, manipulate, and master it have shaped civilization. From the sundial to the atomic clock, from calendar reform to GPS, we trace how human ingenuity has made time visible and controllable, and how in doing so we've both expanded our reach and deepened our entanglement with its flow. The story of civilization is, in many ways, the story of timekeeping. Long before the invention of writing, humans watched the sky. They saw the waxing and waning of the moon, the slow tilt of seasons, the dance of stars across the heavens. From these movements, they inferred patterns, order in the chaos, cycles that could be predicted and relied upon. Time, once mysterious and abstract, became something they could point to, something they could name. The first calendars were carved into stone, ancient megaliths aligned with solstices, marking the sun's return or departure. In Mesopotamia, early astronomer priests tracked the stars to predict flooding and harvest. In Mesoamerica, the Maya devised a calendar of staggering precision, rooted in both celestial observation and spiritual belief. Across the globe, people built monuments to time. Stonehenge, the pyramids, observatories high in the Andes. With agriculture came the need for coordination, planting, reaping, gathering, all required shared time. Time became social. It became a covenant, a way to unify action. Rulers imposed calendars to bind empires, to assert control. Julius Caesar reformed the Roman calendar to align more closely with the solar year. Centuries later, Pope Gregory XIII corrected the drift of time once more with the Gregorian calendar, which remains our standard today. Clocks changed everything. At first, they were slow, imprecise. Water clocks, hourglasses, sundials all measured time, but not with constancy. Then came the mechanical clock, gears and weights and swinging escapements. Towns erected clock towers, not just to mark the hour, but to declare modernity, to bind their citizens to a new rhythm, one not dictated by the sky, but by the machine. Time moved indoors, into factories, into homes. The Industrial Revolution didn't just change labor, it changed the tempo of life. Workers began their shifts not at sunrise, but at 8:00 a.m. Trains ran on timetables. Synchronization became a necessity. In 1884, the world agreed on a prime meridian at Greenwich, and time zones were born. The earth was carved into slices of temporal order. The 20th century took this further. Einstein showed that time was not absolute. It could stretch and bend under the weight of motion and gravity. This was not just theory. GPS satellites must account for relativistic time differences, or your phone would lead you miles off course. Time, it turns out, is local. Your head experiences a slightly different time than your feet. Astronauts age more slowly in orbit than Those on Earth. The ticking of the universe is not uniform, but dependent on where you are and how fast you move. Still, we crave precision. Today's atomic clocks are so exact they lose only a second every 100 million years. The vibration of cesium atoms has become the standard by which we measure the second. This accuracy powers the digital world, enabling stock markets, data centers, secure communication, even the internet itself. Yet in this pursuit of perfect time, we've also created new anxieties. Always connected, always scheduled, always moving. Our calendars are full, our minutes monetized. We speak of saving time, spending time, running out of time, as though time were currency, not experience. The clock once freed us from chaos. Now it often cages us. Technology gave us efficiency, but it also fractured our days. Notifications, alarms, reminders, 1,000 tiny clocks pulling us in every direction. The sun no longer governs our sleep. The screen does. The body's natural rhythms are overridden by artificial light and perpetual motion. We've gained mastery, but at what cost? Yet, amidst all this, new forms of time emerge. Think of deep time, the timescales of geology, of stars being born and dying, of tectonic plates drifting, or evolutionary time where change unfolds over millions of years, imperceptible to a single life. These vast stretches remind us how narrow human time is. And yet, within our narrow span we build meaning, connection, beauty. There is also sacred time, the time of ritual, of prayer, of Sabbath, moments set apart from the secular rhythm. These offer not escape from time, but a sanctified immersion in it, a way to step back, breathe, and remember that not all hours are equal. Some are fuller, richer. Not everything that matters fits into a planner. The digital age has also given us new metaphors for time. We scroll through it. We stream it. We download memories. In cyberspace, time behaves differently. A message can be sent instantly across continents, or a video from years ago can feel new again. Our timelines are nonlinear. Past and present blur. We live in a web, not a line. This too alters consciousness. Young people today are growing up in a world where now is always layered with the archive of yesterday. Memory is externalized, searchable, clickable. Nostalgia comes faster. The boundaries between moment and memory are porous. But there is hope in this. With awareness, we can reclaim time. We can choose slowness, choose ritual, choose depth over haste. A walk at dusk, a handwritten letter, a quiet morning without a screen. These are small acts of resistance. They remind us that we are not just consumers of time, but creators of it. In the end, all of our tools, our clocks, calendars, apps, are attempts to understand something we never quite control. Time is vast, intimate, relentless, mysterious. It can be measured but never contained. It can be watched but never held. It flows through science and spirit, through story and silence. And always it moves forward. In the next part, we journey deeper into the psychological landscape of time. How do we experience it internally, emotionally, neurologically, spiritually? What happens when our perception of time breaks down? Can we stretch time through mindfulness, or collapse it through focus? What does it mean to live in the present, and can we ever truly do so? To explore the nature of time is to step not only into the realms of physics and cosmology, but into the corridors of the human mind. If time exists out there, unfolding in space-time, it also pulses within us, measured not by atomic oscillations, but by emotion, memory, and attention. Our brains do not tick like clocks. They flow, drift, surge, and stall. Time in this inner domain becomes elastic. Think of how a single minute can feel endless when you're anxious, waiting in silence, the seconds dragging across your skin like cold rain. Or how hours vanish in the presence of joy, as if time folds inward to preserve the moment. This discrepancy isn't imagined, it's deeply biological. Our perception of time is rooted in the structures of the brain, the basal ganglia, the cerebellum, the prefrontal cortex. These regions, working in concert, create a subjective timeline, one that fluctuates with our state of mind. Attention is the gatekeeper. The more stimuli we process, the longer time feels. A crowded moment packed with novelty and sensation is remembered as dense. In contrast, routine compresses time. Days blur together, indistinct and fleeting. This is why childhood summers feel eternal. Every day is new, every experience novel. As we age and patterns settle in, the days move faster, not in reality, but in recollection. Memory, too, is a sculptor of time. We do not remember duration, we remember events. Time is stitched together by what we recall. A year with milestones. Travel, change, love feels full. A year without anchors feels thin. This is the paradox of time perception. The days may pass slowly, but the years fly. A life rich in memory is, in hindsight, longer. This brings us to the elusive present, the now. The past is memory. The future is imagination. But what of the present? Can we dwell there? Neuroscience suggests the present, as we experience it, lasts only a few seconds, sometimes less. Our brain stitches together slivers of time, creating the illusion of continuity. Like frames in a film reel, our consciousness flows from instant to instant, always slightly behind the now. Mindfulness practices attempt to anchor us in this fleeting sliver. Meditation trains the mind to return to breath, sensation, presence. In doing so, time can feel suspended, not stopped but softened. One is no longer caught in regret or anticipation. For a moment, time is no longer an arrow but a lake. Still, reflective, whole. But our inner clocks are not infallible. Disorders of time perception, such as in schizophrenia, depression, or Parkinson's disease, show us how fragile our temporal experience is. In depression, time slows cruelly. Every second feels thick. In mania, it races. In trauma, time can fracture entirely, looping or freezing as the mind attempts to process what overwhelms it. In dreams, time dances. Hours of dream experience unfold in minutes of sleep. Time compresses, expands, rewrites itself. Lucid dreamers sometimes learn to manipulate dream time, experiencing long narratives in short spans. This has fascinated scientists. Is our perception of time purely neuronal? Can time be bent by consciousness alone? This question echoes beyond psychology into spirituality. Mystics across cultures describe states of timelessness, moments of transcendence where past, present, and future collapse into a single awareness. In such states, time is not lost but unified. Eternity is not forever. It is the ever-present now, stretched to encompass all. Philosophers, too, have long wrestled with time's duality. Augustine wrote, "What then is time? If no one asks, me I know. If I wish to explain it, I do not know." For him, time existed not as an external entity, but as a feature of the soul. Heidegger saw time as fundamental to human existence. We are beings toward death, and it is our awareness of finitude that gives life its urgency. Today, modern philosophers ask whether time is real at all. Some theories in physics suggest time is emergent, that it arises from more fundamental interactions, much like temperature arises from molecular motion. In the block universe view, all moments of time exist simultaneously. Past, present, and future are equally real, like frames of a film strip. We move through them, but they all exist at once. If this is true, then what does it mean to choose? To change? If the future is already there, are we merely spectators? Or do we, by observing, by remembering, by acting, collapse possibility to reality? Quantum mechanics suggests that observation matters. Perhaps time is not a river, but a story, and we are both the authors and the readers. But beyond theory, time remains deeply personal. It is the canvas upon which we live. It is the silence between notes, the pause before breath, the hush before dawn. Time is the shape of longing, the shadow of memory, the rhythm of a heartbeat. Beside yours, we do not possess time, but we are shaped by it. We do not understand it fully, but we feel it in every cell. And so, as we come to the end of this journey, we find ourselves not with answers, but with wonder. Time is not merely a ticking clock or a cosmic arrow. It is a mystery lived, a rhythm danced, a question asked by every life that ever was. But our exploration is not quite done. In the final part of this story, we will gather the threads from the stars to the neurons, from Einstein to the inner child, and ask, what does it mean to live with time? To befriend it, rather than race it? To find beauty not in escaping time, but in embracing it fully?